Okay, so today what we're going to be talking about are series. And so I want to start by reminding you of sequences that hopefully you were able to take a look at last week. And then we'll talk about how series can be thought of as a special kind of sequence, really, even though a lot of times people talk about them as though they're these sort of totally separate things, and I understand why, and we'll talk about why, but in a lot of ways, they're really very closely related to sequences. So remember, a sequence, well, a sequence is really just an ordered list of numbers, an infinitely long ordered list of numbers. And so we write out some sequence, maybe xi's, where I is a whole number or maybe a natural number. Remember, natural numbers start at 1, so we count 1, 2, 3, 4, and so on. Whole numbers include 0. So sometimes when people make sequences, they like to start the I here at 0. Sometimes they like to start it at 1. It kind of just depends upon the context of what we're doing, okay? And so either is acceptable, both are considered sequences, it doesn't really matter. Now, the thing about sequences is you can actually think of a sequence really as a function of the natural numbers. Or possibly of the whole numbers, depending upon what we're doing. Because you can really think of xi as evaluate this function at some particular index I. In other words, evaluate this at some number. Well, this is a list. If I input a given value for I that is a whole number or a natural number, this gives me back a number. So yeah, this really is a function of some kind. And the domain of the function is going to be the whole numbers or the natural numbers, depending upon which one we're talking about here. So really, sequences can be thought of as functions. And one of the things that you saw last week is that because of this, even though they are a function with a discrete domain, and therefore most of the limits that we would like to talk about don't really make any sense. Well, they do make sense, but they're not really very interesting. One of the things that is of interest is we can still talk about the limit at infinity. So we can still talk about, for a given sequence, we can write something like the limit as I goes to infinity of xi is equal to some number L. And we define this to mean that for any chosen value of epsilon bigger than 0, there is an m such that when I is bigger than m, the difference between L and xi is less than epsilon. Now, if you think back for a minute to calculus 1, if you think back to the limits at infinity that we defined in calculus 1, you'll notice that this is pretty much the same definition. The only difference is that now, instead of dealing with a variable being bigger than m, like a standard variable like we would be used to in calculus 1, in this case, we're dealing with the index I being restricted to be bigger than n. So the point about this whole definition is that for a sequence to converge to L, this just means that we can guarantee our sequence is as close as we would like, and that's where this epsilon comes in. Epsilon is how close do you want to be. We can guarantee we are within epsilon of the limit by just guaranteeing that our index I is sufficiently large. And that's where the M comes into play. M is what it means for the index to be sufficiently large. So maybe in order to get within 1/10 of the limit, I need to guarantee that my index is bigger than 50. But that means as long as we're bigger than 50 on our index, then our elements of our sequence will be within 1/10 of our target limit, and so on. Now, sequences actually turn out to be one of the most useful things in mathematics. They turn out to have all kinds of applications. And the reason really comes down to the fact that we can talk about these limits of sequences. So hopefully you were able to think a little bit about these limits of sequences last week and kind of get some intuition for what happens when we're thinking about sequences. Now, I want to start talking about series here, which are related, but they are a little bit different than sequences. So a series, or an infinite series, assuming that I can spell, a sequence is really just a list of numbers. Well, a series is going to be a sum of a list of numbers. And so we write it this way. We write it as the sum, and then we put an index, and that index might start at 1, but it might also start at 0. So some people start it as, like, again, it's one of these things that it just depends upon the context. Sometimes we want to start the index at 0. Sometimes we want to start it at 1. And then we put an infinity on the top. And then we put the list of numbers here. So we put some kind of a sequence on the inside. And the way that you want to think about this is it's sort of like an infinite sum. We're trying to sum up an infinite list of things. So we want to say that intuitively, this would be equal to x0 plus x1 plus x2 plus, and so on and so forth, okay? Going on and on like this. And when we are looking at this series, then the problem is that it doesn't make sense to talk about adding an infinite list, okay? Strictly speaking, addition is a binary operation. It takes two things in and it gives us back a number. It takes two numbers, it combines them into a sum. You can't talk about summing an infinitely long list. You can talk about finite lists, because for a finite list, I can break down the sum into pairs and do one pair at a time. You cannot talk about an infinite sum, not at least simply as an arithmetic operation. So instead, here is the way that we define the outcome of a series. And it's actually, if you spend some time thinking about it, this is kind of the obvious thing to do. So we define the nth partial sum, and let me write that down here, nth partial sum, Sn, to be equal to the sum from I equals 0 up to n of this sequence of xi's that we are adding together. So this is a perfectly well-defined thing because this is a finite sum. This is just going to be x0 plus x1 plus all the way out to xn, but it stops after the nth term in the sequence. So this really makes perfect sense. There's no difficulties here. Let me see if I can get this glare to be any better. I'm not really sure if I can or not. Might be better if I just turn off those lights entirely, but we'll see. Hopefully I'll be blocking most of the glare as we go. So the partial sums, these are perfectly well defined. And then what we're going to do is we're going to define the outcome of this series. Yeah, let me just turn off this light. I think that'll be better. we're going to define the outcome of this series to be equal to the limit as n approaches infinity of the sum from I equals 1 up to n of these xi, which is actually the limit as n goes to infinity of these partial sums Sn that we defined down here. So actually all that we're doing really is we are taking the partial sums and then we're taking the limit of them. And notice that these Sn's, the partial sums, these form a sequence. And so it makes perfect sense to talk about the limit of these partial sums, because we can talk about the limit of a sequence, and therefore everything is fine. Now, this is what an infinite series is. The truth is that you are familiar with infinite series. You've been working with them for many, many years. You just may not have realized it. And an example of an infinite series is a decimal expansion. So decimals are infinite series. That's the way that they work, okay? They're actually just an infinite series. They are a way of expressing a number as an infinite series. And why are they an infinite series? Well, the way that you think about this is each decimal place expresses the next thing that you're going to add. Like, let's say that I have something like 3.14159 and so on, right? This is a decimal expansion for pi, just the first few digits. Well, this is actually going to be 3 plus 1 over 10 plus 4 over 100 plus 1 over 1000. And we keep on going like this, right? But we keep on adding something in at each step. And so really, this is just an infinite series. And in fact, you can think of any given decimal number as an infinite series of the form sum from I equals 1 to infinity of some decimal numbers from 0 through 9 times 10 to the minus I. And then, of course, you have a whole number part as well. But if you're just talking about the part after the decimal, then this is what you get. Now, how do we know that these are going to converge? Well, the answer in terms of these converging for the decimals is it's actually not too difficult to see that they converge. The reason why they converge to something is because notice that the partial sums form an increasing series. The reason being that when you're doing a decimal expansion, and let's, for the moment, we'll just think about positive numbers here, although for negative numbers, it's pretty much the same thing. Well, each time you are adding something, maybe you're adding 0, but you're definitely not subtracting anything. And so the partial sums are always increasing. But furthermore, the partial sums are bounded above. In other words, you can never get above a certain limit. And the reason is because if I think about the sum from I equals 1 up to n of xi times 10 to the minus I, if you think about it, I can never make this sum larger than 0.999999 out to n copies of 9s, okay? That is the largest that this sum could ever be if I'm choosing these xi's to be the digit 0 through 9. So therefore, these partial sums are going to be bounded above by 1. Well, it turns out that if you have a non-decreasing sequence, in other words, each term in the sequence is getting larger, or at worst staying the same, and it's bounded above, then it turns out that it has to converge to some real number. And it's not too difficult to see that that's going to be happening, right? You are essentially, think about the squeeze theorem. Now, you have to be a little bit careful there because technically speaking, there are some issues that you can encounter. For instance, among the rational numbers, it doesn't have to converge. Like, this doesn't have to converge to a rational number, but it does have to converge to a real number. And so every decimal number is going to converge to some specific number. Now, another interesting thing, and we'll see this even more clearly in a moment, is this sort of definition tells me how to define decimal numbers that are repeating. Like, what is 0.9999999? Like, what is 0.9 repeating? People often find this sort of thing a little bit confusing. What in the world does this actually mean? Well, it turns out that 0.9 repeating is actually strictly equal to the number 1. And why is this true? Well, the reason is because I can make the partial sums be as close to 1 as I want just by requiring that I take sufficiently many digits. If I want to get within 1,000th of 1, I would simply need to make sure that I have a minimum of 3 digits. If I wanted to make sure that I'm within 1/10,000th of 1, I would need to make sure I have a minimum of 4 digits. But I can guarantee that, you know, the 0.999 whatever, however many I go out, as long as I require there to be enough 9s, that is going to be a number that is close to 1. No matter how close I want to get to 1, I can guarantee that I do it. And therefore, 0.99999 repeating is a series that converges to 1. Okay, so now that we have some idea of what series are, and now that you've hopefully seen how, yeah, in fact, we have seen series before. They're not, maybe we haven't seen them in that context, but we have seen them. I want to talk about some specific types of series. Now, really quick diversion before we get on to a specific type of series. I want to mention that actually one of the ways in which series play an important role is, well, technically they're considered sequences in this context, but is in constructing the real number system itself. So the real number system, in order to make the real numbers, it's not really an obvious thing to do, okay? So when we're going from, say, the integers to the rational numbers, that's sort of an algebraic operation. Because think about what you do to go from the integers to the rationals. What you're really trying to do is you throw in fractions. And throwing in fractions, that really means throwing in numbers that solve equations. For instance, the number 3/5 is going to be the number that when you multiply 3/5 times 5, you get 3. So you can think of it as trying to solve the equation 5x is equal to 3. So when you throw in the rational numbers, it's this algebraic kind of thing. You're asking for solutions to equations that look like this. And similarly, when you throw in certain irrational numbers, you can think of it algebraically, like x squared equals 2. This you have to throw in the square root of 2. Well, here's the problem. It turns out most real numbers cannot be obtained in this way. In fact, to get most real numbers, we have to define them as the limits of sequences or series involving rational numbers. And this leads into a very interesting construction in mathematics called Koshi sequences. And it turns out that one way to construct the real number system is to define the real numbers in terms of these Koshi sequences. And one way to think about these Koshi sequences, they're a little bit more general, but really these Koshi sequences are, one type of Koshi sequence is a decimal expansion. And so Koshi sequences makes precise the idea that the real numbers are given by decimal expansions. There's other ways of getting the real number system, by the way. This is not the only one. There's also an approach due to a guy named Dedekind, who constructed the real number system in a slightly different way. And it turns out that the two constructions are equivalent, although not obviously equivalent. But yeah, so the point is that we can make precise this idea that the decimal expansions, which are really series, can be used to define the real number system. And they do, in fact, define the real numbers in terms of rational numbers, because every partial sum for a decimal expansion is going to be some rational number, right? Because it's a finite sum of rational numbers. Therefore, it is itself a rational number. So the issue, the reason that we get beyond the rational numbers in that process is because we end up with these infinite series rather than just having these finite partial sums. All right, so I just wanted to mention that you can actually construct the real numbers this way, and it's actually quite important to do so if you're trying to rigorously define the real number system. But I want to look now at some other types of series, and in particular, we're going to look at something known as a geometric series. Now, geometric series turn out to be one of the kind of nicer types of series to analyze. Now, one of the problems that we run into when we're talking about series is that a lot of series, you cannot actually figure out what the series converges to. But for geometric series, we can actually do it. And so what does a geometric series look like? Well, a geometric series looks like the following. A geometric series is going to be something that looks like a plus a times r plus a times r squared plus a times r cubed, and so on and so forth. This is a geometric series. Now, I want to show you an example of a geometric series, and also, in the process, we're going to solve an ancient philosophical dilemma. Well, obviously, we won't be the first people to solve it. Other people have solved this before, but we are going to see the answer to an ancient philosophical dilemma. So, the first example that I want to do is if A is equal to 1, and r is equal to 1/2. Then what's going to happen with the partial sums? Well, the first partial sum is then going to just be equal to 1 itself. The second partial sum is going to be 1 plus 1/2, which is equal to 3/2. Now, we can make a little bit of a picture here on a number line. So we start at 1, and then we go halfway between 1 and 2. And then for S3, this is going to be S2 plus 1 over 4, because 1/2 squared would be 1/4. But adding 1/4 actually just takes me, from this point, it takes me halfway again closer to 2. And S4 is going to be S3 plus 1 over 8. Well, what is the distance between 2 and between S3? Right, so here's S1, S2, S3. It turns out that the distance here is going to be 1/4. So adding 1/8 is going to take us halfway again to 2. And then what happens at S5? Well, once again, we end up adding half of the distance between S4 and 2. And so what we end up with is a sequence of partial sums that is getting closer and closer to the number 2, but never quite reaching it. And as a result, what we can say is that the definition of an infinite series is the limit of these partial sums. So we can say that the sum of 1 times 1/2 to the I from I equals 0 up to infinity is actually going to be equal to 2. Because in the limit, these partial sums are getting closer and closer to 2. Now, how does this relate to an ancient philosophical dilemma? Well, the dilemma is something called Xenos Paradox. And Xenos Paradox is named after the Greek philosopher Zeno, who believed that motion was an illusion on the grounds that he couldn't understand it. Basically, he was clueless and he assumed that the entire world must conform to his limited comprehension. So, yeah, frankly, I am not a big fan of Zeno. Guy made some massively silly mistakes. What was his mistake? Well, the reason that he argued that motion was impossible is because he said, suppose that you want to move from 0 to 2. Well, then you have to move through 1. And then you have to move through 3/2. And then you have to move through 1 7/8, and so on and so forth, right? There's an infinite number of points that you have to go through. So he said that means there's an infinite number of moments in between each one of these things, and that would be impossible. Now, you can probably see where the problem with that argument is. The problem is that, yeah, there's an infinite number of points of time, but that's not a big deal. It's just that when you add together all of those times, it comes out to a finite number. And we can make that precise with this idea of infinite series. When you add together the time that it takes to do each one of these steps, the total time is finite, even though there's an infinite number of stages in between. And so the solution to Zeno's paradox is very simple. The solution is that some infinite series converge. In other words, there are infinite sums that converge to a finite number. And that is perfectly fine and normal. And in fact, if you think about where his paradox comes from, you might even be able to think of that solution without talking about series, because yeah, really, all he's observing is that there's an infinite number of points that you pass through on the number line as you try to move. Well, so what? We go through an infinite number of points. Big deal, right? It's not like that's any kind of massive revelation here. And the observation, though, is simply that even though you move through an infinite number of points, you've only moved a finite distance in a finite time. Because the length of time and the length that you've moved are both finite, even though you've moved through an infinite number of points. So, like I said, I am not a big fan of Zeno. Guy's really famous for making a really silly mistake, basically. Anyway, so this is an example of a geometric series. Now, let's talk about geometric series in general and what we can say about them. So, let's say that what we have here is we are trying to deal with the sum from I equals 0 to infinity of a times r to the I. So this is going to be equal to a plus a times r plus ar squared, and so on and so forth. What can we say about this? Well, it turns out that we can actually write this down in a closed form. And the way that we're going to do this, the way that we can write down a closed form expression, is I'm going to consider the nth partial sum, which is the sum from I equals 0 up to n of a r to the I. Now, what is this going to be equal to? Well, I can say that this is going to be equal to A plus AR plus all the way out to AR to the N by definition. Now, this is where things get really clever. There's a clever little trick that we can play here. We can notice that R times S to the N, this would be equal to RA plus, well, actually, let me write it this way. It would be AR plus AR squared plus all the way out to AR to the N plus 1. So if I were to write Sn minus R times Sn, then when you compare these two, every single term in the first list shows up in the second list, except this first term and this last term in the second list. So this actually becomes A minus A to the times R to the N plus 1. Because everything else is going to cancel. Make sure that you take a moment to see why that cancels like this. And what that means is that I can say, I guess I kind of need a little more room here, unfortunately. I can say that if we factor out Sn, we get Sn times 1 minus R is equal to A times 1 minus R to the N plus 1. So I factored the right-hand side as well. But this means that Sn is equal to A times 1 minus R to the N plus 1 divided by 1 minus R. Now, why is this helpful? Well, the reason is because at this point, we can see exactly what is going to happen to these Sn's. Because if the absolute value of R is less than 1, then as n approaches infinity, Sn is going to approach A times 1 over 1 minus R. Because this term here is going to go to 0. As you take a number whose magnitude is less than 1, as you start raising that to a larger and larger power, that number gets closer and closer to 0. And so this converges like so. On the other hand, if the absolute value of R is bigger than 1, then the Sn diverge. So in that case, this does not converge. But if the absolute value of R is less than 1, then this is going to converge, and it's going to converge to A times 1 over 1 minus R. In fact, it turns out that this formula also applies by exactly the same argument. You can say that this is true as for complex R as well, as long as the complex number is sufficiently small. So there we go. We can see that this is going to converge. And this really is a proof that it converges, because you'll notice I wrote down a formula here for the nth partial sum. And then I showed that as n goes to infinity, this sequence converges. So this really does prove that the geometric series for r less than 1, or absolute value r less than 1, I should say, does in fact converge, okay? We really have proved that. Now, there's a few observations that I want to make here about this proof. Well, there's one observation in particular. Why would you think to do this? Because that's sort of the question I think that a lot of people have when they see this thing. Why would you have thought to do this in the first place? Well, the reason that you would think to do this is go back to what we did in the case with the A equals 1, R equals 1/2 case. We had this thing where we noticed that at each stage, we were just getting closer to 2. Like we kept cutting the distance in half. If you were to expand that out and look at what is the difference between the different sums, you would notice that the difference between the sums is just going to be 1/2 raised to the nth power. And so then you might ask yourself this question of, can we actually write down what those partial sums are and see what happens to them? And in the process of doing that, you might notice that actually there's nothing particularly special about the 1/2 showing up as r. The whole argument really carries over for other values of r as well. And so I think that would be one way of getting this. Another way of getting this whole idea would be, oh, give me just a second here.